So now we'll take a look at 6.3, which is trig identities. The definition of a trigonometric identity is a trigonometric equation that is true for all angles, provided that both sides of the equation are defined for that angle. So we just finished a section on trigonometric equations. For example, sine x equals pi over 2 minus x. Now, in order to do this, we could solve this problem by graphing the left-hand side as well as the right-hand side of the equation. Let's just try that out on the graphing calculator right now. Go to my graphing calculator and I graph sine x as well as pi over 2 minus x. I'm looking for where those two graphs cross. So there's my basic sine shape. I've got a trig zoom right now. So if you go to your zoom menu, choose number 7, zoom trig. And we can graph that out here. So sine starts in the middle, goes up, and comes back after 2 pi. Okay, so this is my basic trig window from 2 pi to 2 pi, negative 2 pi to 2 pi, negative 4 to 4. And then my line pi over 2 minus x is a straight line with a y-intercept of pi over 2 and a slope of x of negative 1. And then those two cross at one point, and this is called the solution. So with a trigonometric equation, we try to solve for x. The intersection of the right-hand side and the left-hand side. Now if you have a trigonometric identity, if we graph the right-hand side, sine x, or left-hand side, and the right-hand side, sine pi minus x, let's take a look at what that looks like. So sine x, and then sine pi minus x. Okay, so there's my sine x. Where's my sine pi minus x? I don't see anything. And it tells me it's finished. So maybe I can change, if I go left here, I can change press enter and it'll make my graph nice and dark. So let's try that again and see. There's sine x. Now my sine pi minus x should be nice and dark. Ah, there's sine pi minus x. Sine pi minus x is exactly the same as sine x. You can actually go left and push enter many times and you get different sorts of shapes. One that shades under or over. I like this one. It looks like a ball. So here's sine x. And here comes sine pi minus x. So this time if I graph the left-hand side and the right-hand side, they're the same for all values of x. So here's my sine graph. Again, just using a standard zoom trig window from negative 2 pi to pi, negative 4 to 4. And my sine pi minus x is exactly the same. Now why is that? Well, I'd have to actually factor the b value, so take out the negative sign. This is the same as sine negative x minus pi, which is a reflection in the y-axis and then a translation pi units to the right. So if I reflected this graph, it would look like this. And then if I moved it pi units to the right, it would line up again with itself, because there's pi between two maximums. Okay, the distance from this point to this point is pi. So with the trigonometric identity, it is true for every x value. Okay, the graphs are identical. And with the trig equation, we've got different graphs for the left-hand side and the right-hand side. So let's take a look at some examples of important identities. First one is the fact that cosine is an even function. An even identity means that if you take the function and you reflect it in the y-axis, then it still looks the same. So if you take this cosine function and you take the left side and draw it on the right side, you get exactly the same graph. So cosine of negative x is the same as cosine of x. An odd function is if you reflect the graph in the y-axis, doing a horizontal reflection. This is the same as reflecting the graph in the x-axis, doing a vertical reflection. So if I reflected this graph using my x-axis as a mirror, then I get this shape. And if I reflect my graph using the y-axis as a mirror, so the right becomes the left and the left becomes the right, well, those two graphs are exactly the same. So sine of negative x and negative sine of x are the same. So if you graphed cosine of negative x, you get the blue line. It's the same as the black one. And now for some further identities. Tangent is the same as sine over cos. Sine squared plus cos squared is 1. Tan squared plus 1 is secant squared. And 1 plus cotangent squared is cosecant squared. All of these identities would be given to you on a formula sheet. You don't have to memorize them. But let's just see why they're true. So if you remember, tan x is y over x. And the y value, if you're on the unit circle, is the sine. And the x value is cosine. So tangent is opposite over adjacent. It would be sine divided by cosine. Now why is sine squared plus cos squared equal to 1? Well, remember that sine squared, sine is y over r. So sine squared is y over r squared. Cos is x over r. So we'd have x over r squared. And now if I square the top and the bottom of the fraction, I'll have common denominators. I can put everything over r squared, and on the top I'd get x squared plus y squared. But if you remember from last unit, x, y, r makes a triangle. X squared plus y squared is equal to r squared. It's just another version of the Pythagorean theorem. So instead of x squared plus y squared, I could write r squared. This is r squared over r squared, which is always 1. This is the most useful formula for all trig identities. And the next two are just derived from that one and some of the facts that we know about the definition of tangent and cotangent. So if you want to, you can try to see where those come from, but I won't prove them today. So now we can verify sine or cosine identities using some angles. So we can try and check to see that cosine plus sine squared is always 1. Well, let's check it at the point pi over 3. Pi over 3 is the same as the angle 2 pi over 6, which would be 1, 2. A reference angle of 60 degrees, making a 1, 2, 3 triangle on the unit circle. So sine squared of pi over 3 plus cos squared of pi over 3. We want to see, is this actually equal to 1? So sine of pi over 3 is opposite over hypotenuse, so root 3 over 2. Cosine is adjacent over hypotenuse, so 1 over 2, and then the square. Root 3 squared is 3, 2 squared is 4, 1 squared is 1, 2 squared is 4, and 3 plus 1 is 4. So we get 4 over 4, which is 1. And we can also try this on the calculator using x equals 5. So sine of 5 squared plus cos of 5 squared is 1. And we can also check it by graphing. So if we graph sine x squared plus cos x squared, you can see that the graph looks like the number y equals 1. And in fact, if we graph the right-hand side, the number 1, using my favorite ball function, there it is, you can see that that graph is exactly the same. So first I graphed sine squared x plus cosine squared x. You could put extra brackets to show that this is around the whole function, but you don't actually need to. As long as the squared is outside of the brackets, then it means you're squaring the whole function. And then when I graph the right side, the number 1, it's exactly the same line, proving that, or verifying that these two functions, the right-hand side and the left-hand side, are the same, that this is truly a trig identity. Now, another way to write cotangent x is cosine x divided by sine x, because cotangent is just the opposite of tangent. So we saw that tangent was sine over cos. So cotangent is the reciprocal, cosine over sine. Now if we want to, we can use some of the formulas from above to write this in different ways. For example, if I wanted to write my equation using only sines, I could use the fact that sine squared x plus cosine squared x equals 1. So if I want to have only sines, then I would try to solve this for cosine squared x by moving the sine squared x to the other side of the equation. Then to get cosine x by itself, I could just square root both sides. So cosine x is equal to the square root of 1 minus sine squared x. Technically, I should put positive negative here for every time I take the square root. So now if I want to, I can replace that expression instead of cosine x in my formula. And now I have a way for writing cotangent x that only uses sines. Now I could solve this equation in the same way, except for isolating sine on one side. If I wanted to, I could move the cosine to the other side and get the same sort of form of the solution. And then I could replace all the sines in the original question with cosines. So there's two new ways of writing cotangent, using only sines or only cosines. And we can check that this is true just by putting in a number like pi over 4. So let's see, what is cotangent of pi over 4? That would be 1 divided by tangent of pi over 4, which is 1. Now I could check some of the other forms. Cosine pi over 4 divided by sine pi over 4 is also 1. And I could even do this with my very last equation. This is showing that it works for one value. And if you wanted, you could graph all these functions as well, and you'd see that all of them have the same shape. So everything is equal to 1. Regardless of which function I use. These give the same values for any x coordinate. So to practice, take a look at section 6.1, page 264, number 1, and page 266, numbers 5 to 7.